6, we're going to talk about the idea of inverse function. And so to make this super simple, let's just start with what in the world is an inverse function. So let's say you had a function x plus 4. F of x equals x plus 4. That is that every time you have an x, you're going to add 4 and you're going to generate some y. So let's say we had a set of numbers a that'll serve more or less like our domain or our x values. And that set of numbers is 1, 2, 3. So if you were to plug them in, 1 plus 4, you would get 5, 2 plus 4, 6, so on and so forth. You would basically have this other set of numbers, b. So what we can say is it's a set of ordered pairs. Basically, f of x, x plus 4, would be some set of ordered pairs, 1, 5, 2, 6, 3, 7, 4, 8. And that's just a set of numbers, okay? When we use the idea of inverse of a function, okay, what we're going to basically do is take these ordered pairs and flip-flop them. So instead of 1, 5, we're going to generate 5, 1, 6, 2, 7, 3, 8, 4, okay? And so this is the notation f inverse, the f raised to the -1, read as f inverse, that we do to basically make an inverse, okay? And so basically that would go from set B to set A. Well, what does that mean? Well, look, the inverse of this function, if this is f inverse, instead of being x plus 4, would be sort of the opposite. How about x minus 4? And notice now if you took the input of 5 minus 4, you'd get the 1. Set B, again, the input now 6 minus 4 is 2, and so on and so forth. So really, in a very simplistic way, an inverse is where you take the domain and the range and you flip them. The x's become the y's become the x's. If you're looking at it this way, instead of set A being your input, now set B is your input. But it's the idea of opposite, okay? So to kind of illustrate this, you can see that, you know, if whatever the domain of f and the range of f, they're going to flip-flop. Okay, the domain and the range are going to basically flip-flop. If you have two functions that are inverses of one another, one of the unique things about them that we'll see is they have this undoing effect, where if I did f of f inverse, so again, what was f inverse? X minus 4. So f of x minus 4, that is to say, everywhere you have an x here, you're going to input x minus 4. X minus 4 plus 4. Notice what happens. The 4's cancel and you're left with x. So when you put a function an inverse into a function, it actually will reduce down to x every single time. Or likewise, if you did f inverse of f of x, that is to say, take the original function and input it in place of x into the inverse, so this becomes x plus 4 minus 4. Again, it simplifies down to x. So this is something we'll see. How do you know if two functions are inverses? Well, sometimes we can just look at them and know, like, what's the opposite of adding 4? Subtracting 4. That's the notion of inverse, okay? But sometimes it's a little more complicated, so you can always input one into the other and see, does it reduce down to x? And if it does, the answer is absolutely, they are inverses. Now, one thing to talk about is, you could say that this is f and this is f inverse, but it's just as easy to say that this is the inverse of this. So it's not just that this is the inverse of that, they're both inverses of one another. So inverses come in pairs is another way to look at that. All right, so example 1, find the inverse of this function. All right, then verify that both f of f inverse and f inverse of f of x are equal to the identity function, that is to say they're equal to x. Well, let's just look at this. What's the opposite of multiplying by 4? The answer is dividing by 4. So this one's so simple, we can literally do it by inspection. So the inverse of this would be x divided by 4, okay? 4 times x, x divided by 4. These are inverse operation. They're also inverse functions of one another. So now let's verify by taking and doing f of f inverse. So that is to say, everywhere you see an x here, you're going to replace it with x over 4. So f of x over 4, 4 times x over 4, the 4's cancel, and yeah, it equals x. And likewise, you'll see the same thing here. So this is a very simplistic example, but it is offering you this idea of inverse, okay? It's an informal way of going about it, and there's a more formal way, especially when the functions get more complicated, that we will look at in just a moment. All right, so this exponent of -1, it doesn't mean that this is the reciprocal, okay? We're not raising it to the power of -1. So this is not the same thing. This f of inverse, f -1, is talking about the inverse, so don't get confused, all right, by that. All right, find the inverse of the function f of x equals x minus 6, then verify that both f of f inverse and f inverse of fx are equal to the identity. It's the same idea. And again, these are so simple, we can almost just do them informally. So what's the opposite of subtracting 6 from a number? Well, it would be adding 6 to a number. So these two functions should be inverses. And again, you can see this idea of inputting the inverse into the original. So putting the x plus 6 into the original function where there used to be an x, I put x plus 6. And then that minus 6 was part of the original function. And then again, it simplifies to x. And here's the same idea. All right. Now, with a table, we can literally flip-flop. So what do I mean? So here's a table. -2, -8, -1, -7, 0, -6, etc. And if I ask you, what is the inverse of this function? Because I know it's a function because notice all of the x's are different. What is the inverse of this function? Well, literally, you're going to flip-flop. The inverse would be now instead of -8 being the output, it's now the input. -8, -2, -7, -1. So inverse is really, really simple on a table because literally you're just going to flip-flop x and y, or x and f of x if you like. All right, so here's a more formal definition, all right? If f and g are two functions, so two functions, f and g, and you can do f of g of x and get x, and you can do g of f of x and get x, then under these conditions, these two are inverses. So you can call the first one f and the second one f inverse. So instead of calling it f and g, let's call it f and f inverse. Doesn't matter which one's considered the inverse because they, again, are inverses of one another. So the domain of f will be equal to the range of the inverse, and the range of f must be equal to the domain of the inverse. So again, this idea of the domain and the range basically flip-flopping. All right. Example 3. Verify inverses algebraically. Okay, so how do I do that? Well, let's look at these first of all, and you'll notice right off the bat this is a little bit more complicated. So a quick question. Notice the three operations happening here. You got multiplication by 2. You've got raising to a power of the third, okay, raising to the third power. And then you've got subtraction. So let's just talk about what would be the three opposites. Well, the opposite of multiplying by 2, you're going to have some sort of division by 2. What's the opposite of raising to the third power? Well, that would be taking a cube root. And then what's the opposite of subtracting 1? Adding 1. So if you notice here, you see those three operations. Now, the order does matter. So you might not want to just jump in doing this by inspection yet, but eventually you would understand that in order for these to be inverses, this cube root would have to cover the whole thing, taking the cube root of the whole thing, and this -1 is going to be actually a +1, and then the whole thing needs to be divided by 2. And it has to do with the solving process that we'll look at later on. But we want to just, in this case, they're giving me two functions, and I want to know, are they actually inverses? So let's find out. What is f of g of x? So f of this whole thing. So this whole thing goes in place of x right here. So we have 2, and then this whole thing raised to the third -1. Well, right off the bat, the cube root and the cube are going to simplify or cancel. And then the 2 and the division by 2 now cancel. And then the +1 and the -1 cancel, and lo and behold, I get x. So I'm feeling pretty good. Hey, these are probably inverses, but we have to actually check both directions. So let's go ahead and do g of f of x. All right, so this f function here is going to go right in here in place of x. So notice under the radical, under the cube root, this goes here, and then start simplifying. All right, these 1's are going to cancel. The 2's are going to cancel. And then the cube root of something raised to the third, those are going to cancel. And I again get x. So yes, I verified it. Yay for math. They are inverses of one another. 4, it says which of the functions is the inverse of this one. So now we got basically 2 to choose from. Now notice we talked about this idea of you got x, subtraction of 2, so there's going to have to be some sort of addition of 2, and then you got 5 over this. So one of these is going to be the inverse, one of them's not. So these get to a point where it's a little bit harder to just look at them. But let's take a look and see what happens here when we try f of g of x. So let's start with the first one, f of g of x. Putting the g function into the f function. So this goes in place of x. In the simplification process here, in case you've forgotten, it looks a little complicated because you got a fraction inside of a fraction. But basically, whatever this division is here, if you'll multiply both the top and the bottom by that number 5, so the top times 5, 5 times 5 is going to be 25. On the bottom, 5 times this expression will just get rid of the 5, so you'll have an x minus 2. 5 times this will be negative 10. So basically, I'd have x minus 2 minus 10. Well, that'd be x minus 12. And so this actually simplifies down to this, which we can see is not equal to x. So we know for sure this is not the inverse. So obviously, this is probably going to be it. But let's go ahead and check it. Let's do f of h of x. So putting the h function, this guy right here, in place of x. And so here, the simplifying is a lot easier because these 2's will simply cancel. And then whenever you have this idea of division, again, reciprocate or multiply the top and the bottom both by x. Basically, the x is going to cancel out on the bottom. And so you'll have more or less the 5's canceling, and you end up with just x. Okay. So again, basically, when you have this division, 5 over x, the idea is dividing by a fraction. Don't ask why. Flip the second number over and multiply. So multiply this 5 by x over 5, and the 5's will cancel, and you're left with x. So you can see that, hey, that appears to be the inverse function. Remember, to confirm it, you've already done f of h of x. You would need to do h of f of x to make sure that it actually is simplifying down to x, and therefore confirming they are, in fact, inverses of one another. All right, now we've talked about algebraically this idea of one into the other, this composition of functions, but what about graphically? Like, what in the world? Is there a relationship between the graph? Well, we know that if you have the point AB, its inverse will have the point BA. So here's what basically happens. X and Y are flip-flopping, so literally the graph is more or less a reflection over the line y equals x. So in other words, here's the line y equals x, you know, the linear parent function. And if you had some function that you see in this light gray, if you were to reflect it over this line, you would get what you see in the black, the bold there. So look at how these two compare. They are basically reflections over the line y equals x. So that is true of all inverses. So graphically speaking, when we look at two graphs, you can usually tell pretty well whether or not they are in fact inverses by simply looking, are they a reflection across the line y equals x? So for instance, verify that the functions f and g from example 3 are inverses of one another graphically, okay? So what I would do would be graph the f of x and y1, the g of x and y2, and then notice you see that here's what it looks like. So if you want to jump into y3, you can go ahead and put y equals x in there, and you would see this, and obviously those are reflections over that line. So that's how you would, quote, verify them, okay? Now, when you're looking at certain functions, we're going to need to talk about something, because remember, in order for the inverse to be an inverse function, then it also has to be a function in and of itself. Now, I want you to notice here where they put f inverse is x squared. So what's the opposite of a square root function? Well, an x squared. But then they limit the domain for some reason, okay? I wonder why. Well, we'll talk about that in just a minute, but I do want to just interject that right there. That is something that is going to happen. But let's go ahead and look at example 6. Verify that these functions are inverses of each other, and we want to do it numerically. Well, what does that mean? Well, check it out. If I were to put y1, the first function, y2, the second function, one thing I could do is go look at the tables to see, you know, basically are all the x's and y's flip-flopping, but that might be a little bit complicated because you'd be scrolling all around to see, for instance, if you see the ordered pair -2, 4, do you see the ordered pair 4, -2? And you'd have to scroll all around. But here's a quicker way. Jump down in y3 and put y1 of y2. Now, where do I get this y1 and this y2? Well, let me go ahead and pull up my calculator real quick. All right, so I'm going to do this using the vertical. Instead of doing it this way, I'm going to go alpha y equals number 1. And let's go x minus 5. And then divided by 2. All right, and then we've got 2x plus 5. All right. Jumping down here, to get the y1 of y2 business, okay?
Excuse me, teachers. I need about 4 students. Last name beginning with L through the letter R. Please report to the auditorium at this time. Sophomores L through R, report to the auditorium at this time.
All right, to get the Y1 and Y2, I'm in Y3. I can go to alpha trace, and this brings up what's called the Y bars menu. Okay, so there's my Y1, so hit the number 1 or enter, and then parenthesis, and then back to your Y bars, alpha trace, number 2. And so notice what this is doing. This is putting Y2 into Y1. So this is doing the composition of functions. And then let's likewise do Y2 of Y1. Number 2. All right. And so in Y3 and Y4, what I'm going to basically see is, are these the same? All right, so let's go to our table, second graph. All right, and I want you to look in Y3 and Y4. That's what we're really interested in. Every time you put in a -3, you get -3, -3. Every time you put in a -2, you get -2, -2. Every time you put in -1, -1, -1. Well, what does this mean? Well, this means that these are always equivalent. Well, what were these? Well, the composition. So this was like f of g of x. This was g of f of x. If these two are always equal to your x, that's what we've been testing, right? We've been inputting them and seeing, do they end up giving us x? Well, that's exactly what this table is showing you. You always get the same thing, number 1, but number 2, it's also the same as whatever x happens to be. That means that those two functions are, in fact, inverses of one another. So this is a numeric way to attack this question. So algebraically, you input a function to a function, see does it reduce down to x. Graphically, you're looking for a reflection over the line y equals x. Numerically, if you set your table up in such a manner where y3 and y4 are inputting one into another, you're just testing whether you always get the same x value. And you do, and if you do, they are inverses. All right, now we want to talk about whether or not a function actually, an inverse is actually a function. I kind of alluded to this a minute ago. But in order for an inverse function, to have an inverse function, a function must be one-to-one. So what in the world does one-to-one mean? Well, what that means is no two elements in the domain, so no two x values are mapped or correspond to the same element in the range. So let me give you an example of something that is not one-to-one. So take a look at this guy. X squared is definitely a parabola. It is definitely a function in and of itself. However, do you notice how both 1 and -1 are both mapped to the same output, y equals 1? Okay, well, let your brain go somewhere. If that were the case, where I have two different x's corresponding to the same y value, that's okay, that's still a function. You can't repeat x's, but you can repeat y's all day long. But what would that mean about the inverse of this? Well, if these flip-flopped, the ordered pair would be 1, -1, and this would still be 1, 1. But that means now it is sharing x values, which means the inverse of this would actually not be a function. So I kind of alluded to this a minute ago, where I said with x squared, the square root of x is its inverse, x squared, and notice they limited the domain above on that previous slide way up here to x's have to be greater than or equal to 0. In other words, they're only considering half of the parabola. Well, that way its inverse will be a function. But if you consider the whole parabola, so this were not here, the inverse would actually be this parabola that opens to the left. That's a y squared parabola. And then that is no longer a function because it doesn't pass the vertical line test. So what do? We introduce a new test. It's called the horizontal line test. Okay? The horizontal line test is testing whether a function is one-to-one. This one is not. Because if it's a horizontal line here, its inverse vertical line would not pass the vertical line test, therefore it would not be a function, okay? So it's not one-to-one. It doesn't mean we can't do the inverse. It just means that the inverse is not a function. So what do? We restrict the domain so that it is a function, like this example up here. You restrict the domain to half of it so that it is, in fact, a function. And you can see the reflection over the line y equals x there. All right, so let's make sure that we kind of understand what's going on. So in example 7, we're testing for a one-to-one function, okay? So we've got the function square root of x plus 1. Is it one-to-one? Well, let's first of all look at the graphical approach. If you were to graph the square root of x, that's a square root function shifted 1 unit up. So it looks like this right here. It would pass the horizontal line test. So all that means is no y values ever repeat. So of course that means in its inverse, because remember they switch, no x values would repeat. So this is 1-to-1. An algebraic way to test this is to basically take the function and plug in an a and plug in a b, and then see if you can get it to equal a equal b. And so here you would subtract 1 from both sides, square both sides, a equals b. And so if f of a is the same as f of b, that is they both equal a equals b, you can conclude that it is 1-to-1 and does not have an inverse function. I would definitely say this method over here is much easier. Okay, much easier just to graph it and use a horizontal line. And so this is 1-to-1, therefore it would have an inverse. Now the inverse, the opposite of a square root is a square. It would be one of those where you take a parabola. Okay, it goes up like this, but you're only going to use half of the parabola. All right, so how do you find an inverse function algebraically? Okay, they got 5 steps here, but essentially, here's what it boils down to. Okay, you're going to make sure it has an inverse by using the horizontal line test. And then instead of using f of x, let's just put a y there to make life a little bit easier. And then to find its inverse, x and y are going to switch places. So where you had a y, you put an x. Where you had an x, you put a y. And then solve for y. And then whatever you get is going to be your inverse. Okay, so here's an example. Find the inverse of this function. Okay, obviously this is a line of some sort. Its inverse will also be a line. If you graphed it, you could look at it, and lines are definitely 1-to-1. They pass the horizontal line test. All right, so to find the inverse, instead of using f of x, let's just use y. And then here's where the switch happens. X goes here, y goes there. Now solve for y. So I'm going to multiply both sides by 2. I'm going to subtract 5 from both sides. Or actually, they're going to move the 3x this way and subtract the 2x over here, however you want to do it. So this becomes positive 3x, and this 2 becomes negative. And then they're going to divide both sides by 3, so this would be my inverse. Solve for y. So change the y to f inverse. All right. Now you would verify that f of f inverse and f inverse of f would always equal x. And to save a little bit of time, they do. Okay, so those are inverses. So again, you're going to replace f of x with y, do the switch, solve for y, and then replace it back the y with f inverse. And this is how you find the inverse algebraically. All right, sometimes we have to restrict the domain, like I said, on a function like x squared because it's not 1-to-1. But you can restrict the domain, and then you can find the inverse. All right. How about this one? X cubed, all right, passes the horizontal line test. At no point does this particular one. Now, some x cubes don't pass the horizontal line test, but this one does. So let's find its inverse. All right, so again, the process, make this y, do your switch, solve for y. All right, so if the y came over here and the x came over here, that would be negative and that would be negative, but to make life easy, let's just make it positive. So another way to say that is just move the 4 over here, and then if you want to switch the sides, you can, but you don't have to. All right, take the cube root of both sides to get rid of the cube, and it's the whole side, so the whole thing's under the radical, and here is your inverse, okay? And then to verify, again, do f of f inverse and see what you get x. Do f inverse of f, see what you get x. And so we do know that these are, in fact, inverses of one another. All right, example 10. Find the inverse of this square root function. All right, as I already mentioned, this is going to be square root. Its inverse is going to be a square or a parabola. So we're going to have to restrict. But let's go ahead and just do the process. All right, so replace that with y, flip-flop those. Okay, then we're going to square both sides, get rid of the radical. We're going to add 3, so this becomes x squared plus 3. And again, they're switching sides on you. You don't have to unless you want to. And then divide both sides by 2. So if you just put this as your answer, it's actually wrong. Why? Because this is a parabola, and it itself does not pass the horizontal line test. So what you can do is only use half of the parabola. So let's go x is greater than or equal to 0, and you would see that this would be a parabola up in here somewhere. And that's the reflection across the line y equals x. So you're going to have to restrict the range the domain of these in order for it to be one-to-one so that you can actually find the function. Please don't let this piece of it become confusing. You'll notice that if you graph this parabola, if you want to find the part that goes from here to here, which is what we're looking at there, this is the obvious choice, okay? This is the obvious choice. All right, so as we come to a close, I hope this made sense. I know that 10 examples always seems a little overwhelming, but basically to find your inverses, you're going to flip-flop x and y and solve for y. And then again, sometimes you got to restrict your domain if it's not one-to-one. So I hope this makes sense. Go ahead and get started on your assignment.